Hey, have you ever really stopped to think about how all this works? I mean, the words you're reading, the images you see. How does a machine actually understand any of it? Well, it all comes down to language. And today, we're going to break down the secret languages that let us talk to our computers.
See, at its very core, every single computer is just a giant collection of tiny switches. They can either be on or they can be off. That's it. So the huge question, the puzzle we're going to solve today, is how do we get from a simple on or off to the incredibly rich digital world we use every single day?
So, what we're really talking about here is a massive translation problem. We think in one way, and machines, well, they think in a completely different, way simpler way. Let's take a look at just how different they are. So on one side, you've got us. We grew up using the decimal system, base 10. We have 10 digits, 0 through 9, and it just feels natural. It's how our brains are wired. But computers, they run on electricity. And for any circuit inside that machine, there's either a signal flowing, on, or there isn't, off, just two states. That's the gap we need to bridge. To make that leap, we have to learn the computer's native language. And it's a language built entirely on that super simple idea of on and off. It's called binary. Let's start with the absolute smallest building block, the bit. A single bit is the tiniest piece of information a computer can understand. It can only have two values, a 0, which means off, or a 1, which means on. It is literally the atom of all digital information. But a single bit by itself isn't all that useful. It's like having just one letter of the alphabet. So we group them together. The standard grouping is a byte, which is just a team of 8 bits. So if bits are the letters, you can think of a byte as a standard 8-letter word that computers use to build everything. And this is where the magic really kicks in. Watch what happens when we start stacking these bits together. With just 2 bits, you can already make 4 different combinations. Add one more, just 3 bits, and now you have 8. By the time you get to a full byte, that's 8 bits, you can represent 256 completely unique values. This is it. This is how we build complexity out of pure simplicity. Okay, so computers are totally cool with these endless streams of ones and zeros. But for us humans, oh man, it's a total nightmare to read. So we came up with a kind of shorthand to make our lives a whole lot easier. Seriously, just picture it. Staring at a wall of text that's nothing but ones and zeros, trying to find one single mistake. It would drive you crazy, right? This exact problem is why we developed systems that are easier on the eyes, and the main one is called hexadecimal. And check this out. This is the brilliant solution. Hexadecimal, or base 16. It uses our normal digits, 0 through 9, but then it adds the letters A through F to represent the values 10 through 15. Now, the real genius here is that one single hexadecimal digit represents a group of exactly 4 binary digits. It's an absolutely perfect shorthand that makes code way more compact and easier for us to read. So you might be asking, when do you actually use these things? Well, each system has its sweet spot. Binary is perfect for those simple on-off choices, like a setting that's either true or false. Hexadecimal, on the other hand, is a programmer's best friend. You know that perfect shade of blue on your favorite website? Yep, that's probably a 6-digit hex code at work. It's also used to pinpoint exact locations in a computer's memory. All right, so we've got numbers down. We've gone from simple on-off switches to complex numerical values. But what about, words? The stuff we're actually reading right now. That's the next piece of the puzzle. The granddaddy of them all was ASCII. You can think of ASCII as the first digital dictionary. It created a standard map where specific numbers, represented in binary of course, corresponded to letters, symbols, and punctuation marks. For instance, the number 65 was mapped to a capital A. For decades, this was how text worked on computers. But ASCII had this one huge problem. It was built pretty much just for English. In a world with a global internet, that was just not going to cut it. And that's where Unicode comes in to save the day. Unicode is the modern standard that explodes that dictionary to include characters from just about every language on Earth, from Cyrillic to Japanese, and yep, you guessed it, this is how we get all our emojis. All right, that was a lot to take in. You've seen the whole journey, from a single switch to a global language. Now, let's do a quick knowledge check. Just a couple of real-world scenarios to see if it all clicked. Okay, scenario 1. A developer needs to store a simple yes or no answer in their program.
Based on everything we've talked about, what's the most direct, most efficient system to use for a simple two-state problem like this?
And the answer is binary, of course. Its entire structure is built on two states, on or off, 1 or 0. It's a perfect one-to-one match for a yes/no or true/false value. It's the cleanest, most efficient way to do it.
All right, next one. This is a super common problem you might have even seen yourself. You're looking at a web page or a document, but some characters, maybe Cyrillic ones, are just showing up as weird boxes or scrambled symbols. What's going on and what's the fix? This is a classic encoding issue. The hero of this story is Unicode. The problem is that the document is probably using an older standard, like ASCII, that has no idea what those Cyrillic characters are. Switching to Unicode gives the computer the massive dictionary it needs to understand and display those characters correctly.
It's pretty wild when you really think about it, isn't it? Every single thing you're seeing on this screen, every click you make, every letter, every single color, it all starts as a simple on or off signal. It's all just a series of brilliant layered translations. It really makes you wonder, what else will we be able to translate next?